First of all, let me turn the floor to Essie, who my co-organizer, for some initial words, whatever you'd like.
Thank you, Stephen. I'm just so grateful for everyone to make the time and join us. I think exciting times for policy, but especially for getting people out of poverty traps, and mobility is a big part of that. We're putting it, we've been a team together, having a conversation, and so somewhat selfishly we have this to extend the conversation to a lot of people who've been major figures and new researchers in this area. So I'm definitely looking forward to spending the next couple of days with Stephen and this wonderful group. Glad to be here.
Well, most important, thanks to all of you for participating, either in giving papers or being part of the audience. And before we go on, we have to thank the real boss, which is Carrie Cardoza, who's done an incredible job organizing everything and has limitless patience in dealing with absent-minded professors, but various stripes. And on that category, I certainly, I think I personally rank #1. Essie may be a close #2, but I'm Gary, thank you so much. And so again, welcome to all of you. We might as well get the presentations going. Carrie, I have control of the. I can take over the screen.
Yeah, you should have the capability to share screen at the bottom.
Okay, great. Okay, so Essie and I have for the conference was to bring together people who are methodologically oriented and more empirically oriented to talk about new dimensions of intergenerational mobility and ways that that we should think about making progress on these foundational topics. I think it is a fair statement that, well, it's an obvious statement that intergenerational mobility has exploded in the last decade. I think it's also a clear statement there's been enormous progress on the empirical side, but at the same time, I think it's also reasonable to say that work on the theory and methodological sides has probably not been as growing quite as quickly. And so we thought by bringing methodologists and empiricists together, hopefully create some synergies and suggestions for new research. So can everybody see my screen?
Yeah.
Okay. All right. Thanks. And so in the introductory comments are going to be not terribly introductory in the sense that it's going to give some outline for work. The theory of comparative advantage on this paper is that Larry Bloom and Sasha Lukina, and Sasha is a brilliant postdoc at Harris, have done all the intellectual heavy lifting, but be the glib one to give the presentation. But the serious thing is that they really have thought very deeply about the theoretical issues. And so what I want to do in this brief talk is sort of tell you about the work that we're in process doing. And it will be the one talk here that will be theoretically oriented in the sense that I want to put a theoretical model on the table that we've been working with that hopefully has some interesting empirical suggestions as how to proceed. So the basic idea of the paper, and this is a curve I know is going to be repeated over and over again in the conference, is to take as background the great Gatsby curve and the linear approaches to intergenerational mobility, and then ask how might one think differently through the template of theory. And in essence, what we're going to do in this paper is we're going to propose, or in this work, what we are doing is developing some theoretical structures that help generate phenomena such as the Gatsby curve, and they will do them in ways that will be suggestive, unsurprisingly, of moving outside linear frameworks. Now, what does that mean theoretically? In thinking about theoretical models of intergenerational mobility, one dichotomy would be between family models and, I'll say, social models. models. And so we're not going to here talk about neighborhood effects and social interactions and things. And then within family models of intergenerational mobility, the workhorse models look at the ways in which parents invest in children, and then under some set of credit constraints or limits to borrowing are going to generate persistence. And so in the classical literature, which would be Becker and Tomes and Lowry, you have certain assumptions about the nature of technology and the like, and they generate either Markov or related dynamics for the mobility process. And so what this paper is going to do is it's going to live on, start with that as the approach, and then evolve it in a couple of important directions. I think that with reference to those models on the substantive side, part of what we want to do is have a way of thinking about phenomena such as poverty traps or affluence traps that emerge as descriptions of the stochastic process for intergenerational mobility in ways that will differ from the way you might sort of force them into a Becker, Tomes, or Lowry framework. The part that is still under analysis, I think it's fair to say, at least progress, is thinking about competition between families and moving from human capital investment in isolation as the determinant of offspring income to thinking about the way in which there's assignment of individuals across occupations, so the whole distribution matters. So the model is going to be a very simple one logically, which is that there's going to be parents who are going to have some notion of wealth that's going to determine the human capital or the capital of their children, and that process is going to be mediated by shocks. And so there's going to be some process by which you have the evolution of this stock stochastically across generations. Now, what's going to make this? You could say, well, it looks exactly like Becker and Tomes and Lowry type models. So that's stuff that's been around for 40 years. What's going to make this different is the way in which we specify the underlying technologies which describe how individual family dynasties evolve. Now, in saying that, there's going to be a couple of points that are important. First of all, we're going to take stochasticity seriously. And what I mean by that is that in the analysis, I don't think the following statement is unfair about the theories of intergenerational mobility, and that is that the way that they conventionally think about poverty traps or affluence traps is from the vantage point of deterministic models. You have no shocks, so you just say, here's a difference equation, and you ask something about the number of steady states associated with it. Here we want to take stochasticity seriously, and that's going to mean that you actually need a different, and it's going to, the conclusion of that is you don't have a straightforward generalization of poverty traps in multiple steady states from deterministic to stochastic contexts. And so that's going to be more than just an observation that one has to have stochastically defined notions of these things, but actually there'll be different phenomena to look at. So that's kind of the first thing we'll be underlying the analysis. And the second thing is that we want to think about technologies which are a little bit different from or maybe not so much different from those that are conventional. So what that means is that from the vantage point of the decision problems of the families or parents, the first part on preferences is going to look relatively straightforward. And so all of this notation you can translate it into English. All you would say is that parents have some wealth constraint, and they divide the consumption between their own consumption and investment in their children. And there will be a number of assumptions about preferences and the like. Now, for us, this is where the action is going to be in terms of thinking about the theory. We're going to be interested in what I'm going to call the stepping stone model. And in fact, that's the most likely eventual title of the paper. And the idea is going to be that in contrast to the neoclassical model, in which you have this nice continuous variable called capital, or this production function where something happens, there's going to be these discrete capital levels. And what families do is they make these investments recognizing the discreteness of the capital levels. And what that means, in other words, is that for each level of the investment, there's going to be an associated distribution of outcomes for their children. And so that's going to allow for lots of discontinuities relative to the conventional models. And of course, the Becker-Tomes is the smoothest of them all, because it lives with a lot of linearity. Lowry's a little bit more general. But the point is to say that a different way to think about the investment process is there's actually discrete things you do. You move across across a set of threshold values, and that's going to determine that technology tells you something about the investments. Now, I'm looking at Dan Millimet. He might have noticed a discontinuity in investments he started to make the freshman year of college for his daughter. So I can give you, it's easy to think of examples in which you have this notion of discreteness. Why would discreteness be a substantive idea as opposed to a mathematical nuance? Well, the answer is that that's going to be something which is going to naturally generate multiple steady states. In other words, once you introduce these types of non-convexities relative to the standard technologies, that's when you begin to get the action, so to speak, in terms of what a poverty trap might be or what an affluence trap might be. All right, does that all make sense? So the paper is going to make, with respect to preferences, I'm going to say relatively standard assumptions. The only one to note is there's going to be a supermodularity between and wealth, and that's going to matter for the ways in which individuals react to changes in their own wealth. And the upshot is that under those conditions, one can show that there's going to be you come up with results that are going to tell you about the nature of the decision problem and the associated environments in which the individuals are working. And so these are going to be technical assumptions that sort of tell us that the equilibrium, the decision rules, I should say, for the individuals are going to follow the expected properties. In other words, you have non-decreasing investments and the like. Now, this is where the action is going to be. Obviously, on the existence of comparative statics, those sound similar to conventional models. The action is going to be to introduce heterogeneity, and we're going to do it through a particular choice of a probability density, so you can vary parameters of it and say interesting things. And what that's going to generate is an equilibrium distribution of wealth. In other words, you're going to have a set of decision problems for each of the actors. Once you have a population of individuals, you end up with a distribution. And so in that sense, what this is doing is it's giving, the statement that you knew was true for the I'll say the previous cases, and that is that I have a set of stochastic processes for the individual family dynasties. I could take them together and generate a collective stochastic process that has a notion of inequality. All right, now in doing all of that, as I said, that's going to be sort of, I don't want to say standard operating procedure, because that would be, well, maybe it is, but to say that that's kind of going to be the technical background for setting the model. And the upshot of it, and this I say is a essential, I'll even say philosophical idea almost, and Essie will talk about these similar ideas in his presentation. And that is that in talking this way, there's no principal distinction between the thing you call inequality and the thing you call mobility. In other words, the point is that the descriptions of any of these types of environments generates something called a stochastic process. Once you have the stochastic process, if you want to conceptualize something called mobility, you would have a dimension reduction. You take the stochastic process that's its joint probability measure, and you would construct some functional of it. Similarly, any measure you had of inequality, you would do the same thing. Now, why belabor that point? Well, it's because it leads to the idea, which is already known, that the Gatsby curve itself is not kind of a well-posed object. In other words, maybe the more useful way to think is a single thing called a stochastic process. A stochastic process has mobility and inequality dimensions to it. And so whether or not there's a trade-off or not, it's going to depend on the properties of the stochastic process. And so that's going to be the key point for us. In other words, that once we have this nice stochastic process that describes the evolution of the families, one can construct off of it measures of mobility and construct off of it measures of inequality. And the idea that one can lead to the other is unnatural from the stochastic process perspective. I think people have already understood that in the case of linear models. After all, you know, you take an AR1, you know that the variance of the process depends on the AR parameter. So that idea is an old one, I think, in the mobility literature. But one of the things we're going to push here is that one wants to take the stochastic process as the primitive, and then from that adduce anything you want to say about the relationship between the particular, what I call dimension reductions. Okay, so that's going to be kind of the first big piece of background. The second, which is a preview of coming attractions, is going to be the notions of a poverty trap and the notions of an affluence trap. They don't naturally, they don't in a straightforward and easy fashion map from a deterministic world to a stochastic world. In other words, you need to have a somewhat different language for doing these calculations. All right. So in pushing that a little bit harder, what that means is that we then in the analysis are going to go through the both the deterministic and the stochastic models. And so in doing that, of course, if the model is deterministic, this is standard. You know what the arguments are going to be. That is, you have a nice difference equation, and you look for fixed points, and those are the steady states that are going to be of interest. And so this would be kind of the canonical example that you would see with deterministic dynamics. And so you can see what the stepping stone structure is going to do. It's going to give a potential for all these different trapping states and large steady states and the like. All right. Now, in pushing that a little bit harder, one can take the deterministic model and make a couple of observations. Okay, once you have a notion of fixed points, that tells you about steady states. The second is going to be one has to think about attractors. In other words, which steady states are dynamically stable or not. In this case, you can show at least one has to be dynamically stable. And then the second final observation would be that there's going to be a natural ordering to the attractors. And once you have that, then you have a way of defining what a poverty trap would be and what an affluence trap would be. All right. So, how to make the move from the determinist to the stochastic? Well, one way to do it is to say that the stochastic model takes as a special case the deterministic. To do that would be to simply allow the some metric for the noise to move close to zero and see what happens. All right, everybody with me on that?
Steve.
Yes.
Sometimes you fade. I'm not sure whether it's the microphone or the Wi-Fi. Is that what you guys experience too? Yep, your voice fades sometimes.
All right. So what I'm going to do is I'm going to turn the volume up because it
might help.
It must be the Wi-Fi. Now I'm not sure if that will mitigate the times where the Wi-Fi is unstable, but let me at least start with that. Sorry about that. All right. Is everybody kind of with me on what the thought experiments are in the paper? You set up a model in which you've introduced this notion of stepping stones. That's going to create the potential for different dynamics because of the potential for steady states, et cetera. Second thing to do is to introduce stochasticity in a natural way. And then want to understand the relationship between multiple steady states, which are the natural way to think about poverty and affluence traps in the deterministic world, and the way you would think about them in a stochastic world. Okay. So once you take that approach, what you're going to end up with is, in making a segue, kind of as a prior statement, is you'd be interested in thinking about what happens when the noise gets small. And in essence, what's going to happen is the following. And these are really ideas which Larry was pioneered in thinking about evolutionary game theory. And that is, some of these steady states, the deterministic ones, will be probabilistically salient in low noise environments versus others. All right, and so what's going to happen, in other words, is that in these environments, there will be a set of attractors such that as the noise gets small, the likelihood of being at any of the other ones becomes vanishingly, becomes negligible. All right, and so what this is going to do is begin to hint at this idea of stochastic stability. All right, and so then what we have here are just some examples where you could have multiple steady states, and then you could sort of ask what the distribution is of outcomes for different assumptions of the noise. And let me say, if they haven't already, Larry and Sasha should interrupt me freely and aggressively if there's anything I say they don't like. Okay. And so then there's some other, one can then proceed and think through, some of the properties of this model. So in pushing all of this, there's, the upshot for what we call the deterministic stepping stone model is there are going to be some fixed points, some things will be transitory. There won't be any cycles given the assumptions of complementarity and functions increasing, and it's possible to get poverty traps and influence traps. Okay. So this is a description of the, given the time, I'm going to skip these and go directly to what I think is for this audience in particular, the interesting generalizations. So in thinking about the difference between the stochastic and the other, one way to think about the original stepping stone model was you had, this is the output, increase capital, here's the output, and you have literally stepping stones. In contrast, in a stochastic model, what's going to happen is that there will be non-negative random variables that correspond to each of the stepping stones. All right. And so in other words, you're getting a shifting of distributions. First thing to say is a lot of the ideas are going to carry through there. The second thing to say is that one will be able to characterize Markov processes and again, in skipping them in the interest of time and the nature of the presentation doesn't mean these are not there. Some care to work out, you can end up working out the associated Markov processes. All right. Now, with reference to this, one of the things that's nice is that you can actually work with Markov chains because of the fact that you have this discreteness and the associated steps in the stepping stone model. All right, is everybody with me on that? Now, here's where the action's going to be. So far, this was, I'll say this is, this was the theoretical part. When I say that here's the action in terms of the empirics. And that is to ask the question, what is stochastically stable in these environments? That's the first question. And in other words, one of the messages that that's going to be essential in, I think, in making segues from theory to empirical work, we think is essential, is that once you introduce stochasticity, you actually have to think about things differently in a qualitative way. And so an easy example of that is if I have a Markov chain that's 1, 0, 0, 1, that gives me an influence trap and a poverty trap. Once I have 1 minus epsilon, 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 1 minus epsilon, that Markov chain has a unique invariant measure. And so whatever it means, and I don't think the conclusion is going, the actual one is to say no matter how small epsilon is, there is no poverty trap in that universe. You have to ask the questions differently. All right. So operationally, and this is why I made the allusion to think or why stochastic stability becomes an actual question, is that then the way you want to think about data is you ask questions of the form in environments in which you have an underlying deterministic multiplicity of steady states, but you have stochasticity. What are the right measures to identify the probabilistic analog to a poverty trap and an affluent trap? So then pushing that a little bit harder, you might say, well, if I was looking at data across time, I'd like to know which of the regions of the support of the stochastic process do you have concentration of time spent there. Okay, and that's the stochastic stability idea. Once you introduce a little bit of noise, you spend most of your time in one place versus another. All right. And so the upshot of that is one can assess with reference to the deterministic steady states, once you have the stochastic analog, which ones are stochastically stable, which ones are stochastically unstable. And so what the calculations then that are in process are doing is identifying what happens when you introduce these types of perturbations. And so the 1001 is the simplest, maybe a trivial one, but in general, you'll get richer, and you can have situations where you have multiple deterministic steady states, and some of them are stochastically stable, and some of them are not. And so the message for that is, if you're looking in data, you can't simply invoke that something such as bimodality of the cross-sectional distribution because of the presence of multiple steady states. In other words, you have to think differently about what's going to be revealed in the data. All right, does that make sense? Okay. Then I think the final thing, given the time I want to talk about, is the jump ahead is to the following. That is, what does this have to do with the Gatsby curve? Okay, and this is maybe the big message of the paper, and I apologize if I'm jumping around too quickly. Once you have a stochastic process, and we're thinking about kind of the sojourn times in different regions of the support, there's going to be a different set of relationships which exist. Okay. What those relationships are going to do is they're going to link the invariant density to properties of the transition process. So in that sense, that's the Gatsby. That's what we said. Mathematically, the Gatsby curve is always something about the Gatsby relationship has to emerge from a stochastic process. Now, in thinking about it that way, what that means is that you can use the theory of Markov chains to compute specific relationships. And so the one that's reflected here is, if I were to look at two, the probabilities of invariant probabilities of two locations in the process, I could ask the question, what's the relationship between them? And the key result is they're going to have to do with the probabilities of moving in one direction versus moving back. And so this is a balance condition that has to explain the relationship between the fraction of time spent in different states. Rearranging that, this is what the paper is going to argue is the Gatsby curve. And that is that the ratio, or at least a way to think about the Gatsby curve, is that a poverty, a tractor, the key phrase, they're easy to enter and hard to leave. That sounds like Beyond Thunderdome, but that's going to be the key stochastic point. All right. And so in understanding the upshot of stochastic models which have embedded in them these underlying capacities for multiple steady states and the like, what's going to be fundamental is developing the late relationship between the nature of the cross-sectional times, or the invariant time spent in the different configurations, poverty or affluence, and the associated transit probabilities between them. All right, and so in that sense, anything that, and that's what we meant, that every stochastic process embeds in it both the mobility dynamics and the cross-section. All right. Once you think about it that way, one even ends up with a different question to ask for what is persistence. And so what we propose here is to think about it in terms of mixing times. And so a mixing time basically does the following. It says here's an initial cross-sectional density, in this case nu naught. Then you ask, I want to sort of compare it as it iterates through the transition matrix to the invariant measure nu star. You can ask how many, how long does it take to get close to it? All right, initial density is interacting through it, you go to nu star. And what a mixing time does is it says for every epsilon, it gives you the number of time units that it requires the process to get close. Now, the conventional definition of the mixing time is this here, which is you ask basically of all the initial, you ask what's the soup of all of the times it's going to take to get close. So in other words, you search across the different potential initial conditions, and then you take the soup, and that's the definition of mixing time. And those of you that are time series people have already seen analogous ones for in the unit root literature, but this would be the one for Markov chains. All right, so the first point is that this gives you a way of thinking about what it means to say a poverty trap is deep, and that's going to have to do with its mixing time. The second point is that one doesn't have to just have an unconditional mixing time. You can also have a conditional mixing time. I could ask what the difference is between the US mu naught, nu naught, excuse me, and Denmark's nu naught. They will have different conditional mixing times. And so that begins to speak to this deep question as to, do we see greater persistence in one country versus another? Do they have different transition matrices, or are they simply starting in different locations? And so the argument we want to make, in other words, in this work in progress, is that these are the ways one would begin in stochastic environments to construct new statistics, not NU, but NEW new statistics, which would facilitate thinking about persistence across generations. All right, and this is from the movie. I'm going to stop there, since I think it's an unspeakable sin if a co-host goes too much overtime. So thank you. So maybe any questions or anything, Larry and Sasha, did you want to add anything?
So let me add just one thing, and that is that you know, the focus is looking on these attractors as in some sense neighborhoods around them should be poverty traps and all of that. I think it's worth emphasizing that most attractors are not created equal. That when you perform this exercise of driving out the randomness, it is typically the case that only one attractor emerges as the key attractor. So the invariant distributions get spiked around a single attractor, and then you get these little blips elsewhere around the other attractors that disappear at different rates as epsilon gets small. And so that's telling us that we need to think about some kind of notion of metastability for these attractors. They're not really stable states in the dynamical process, but they're in some sense metastable, in the sense that you don't spend very much time around these other attractors, but you spend a lot more time around them than you do around anything else. But it does also suggest that in doing empirical work, if you really want to think about nearly deterministic models, that it's really hard to look at the invariant distribution to pick out some of these metastable states, because they're really going to be small in terms of stationary probability.
Just one comment. In terms of the probabilities associated with these poverty sets and attractors, one would think of the conditional probability, because that's the medium in which you can talk about policy. Right? So if conditional probabilities of being in these attractors have dependencies with instruments, that suggests how one might want to be able to shift them, right?
Absolutely, and there was a slide on that which I skipped.
Stephen, I have one comment too.
Okay.
I like the idea of showing the relationship between the Great Gatsby curve and the poverty trap. But for the Great Gatsby curve, I think people define inequality very broadly and not very accurately. What do you mean inequality in your study is really the rigidity of class boundaries, how easily it is to flow across different income or social classes, and how rigid the boundary is. as compared to some people defining inequality just based on, say, Gini coefficient or other types of indices.
Well, I'm not sure I want to say this model is rich enough to, when I present it, I don't think has some rich thing to say there. What I would say, and what I mean by that is that you're asking a question that decouples this thing K, which was the human capital investment and its interaction from income to something that you might call an occupation or a class of occupations.
Yeah.
Next phase of this, which is hard, where we want to have an assignment model for intergenerational mobility, then I think there's something to say. So the jargon assignment model means that conventional human intergenerational mobility models, parent invests in the child, something happens and that produces the income of the child. An assignment model would say parents collectively invest in their children. There's a distribution of human capital. Once you have a distribution of human capital, there's assignment of people to occupations in the economy. And that assignment process determines associated incomes.
Yeah.
So once you set that model up, you could ask the question about how do the occupation, there you actually do have occupations. And so I could ask that question and then to talk about classes, blue collar or white collar, that would be aggregates of the occupations. So I see, again, I'm a little hesitant to say, yeah, that's how you would do it, because that everything's doing it's the hard part. But conceptualizing it, that's at least how I think one would proceed.
That's good.
Hi, Stephen, from the other Stephen. You talked a lot about steady states in your model, and I'm always bothered by steady states. I doubt if we're ever there. And I mean, it's wonderful analytical convenience, but yeah, I mean, to what extent, in a substantive sense, you know, is this really important, fundamental? Is it's going to screw things up if you're not in it?
Well, I think the part of what we wanted to communicate is that the notion of poverty traps as theoretical objects needs a different definition when things are stochastic. And so some of the measures I talked about, I think address your issue, but I think you brought up a deeper problem, and that is that we want to think about equality along transition paths as opposed to focusing per se on steady states because of the fact that we start far from them. That all said, with reference to what we were talking about, you could say whatever the cross-sectional income distribution is, that's the new knot. You then have a transition process, and there's going to be trade-offs between, there's going to be some speed at which the new knot gets near the steady state. And so that becomes interesting in terms of persistence. Now, the reason I think that's true even is that it answers your question. First, you want to know how long it is. So if it takes a really long time to get to the steady state, that is part of what it means to say that the current configuration of incomes persists. And second, I think that definition actually encompasses the limits of the steady state. In other words, a question you ask is, I have a distribution of income today. To what extent is the system retaining memory of it at t+1, t+2, t+3, et cetera? And that gets away from just focusing on whether there's multiple steady states per se. And so to follow up a comment Larry made, you can have a unique steady state and have arbitrarily high degrees of intergenerational persistence. And that was, and so the extreme case of that's what would be called metastability, which you start in one configuration and it takes quote unquote a very long time to move to the steady state. And so that's actually what we're trying to do, is construct measures that more directly focus on persistence of features of the cross-sectional distribution, as opposed to just asking about the number of steady states. I think, again, I will say from the perspective of theoretical models of poverty traps has been the traditional focus.
Stephen, if I could make a comment.
Sure.
So first of all, I thought that the latter part of your presentation was really interesting because it kind of evokes this old paper, right, in the 90s by Danny Claw, where he was applying like Markov processes to thinking about, inequality and also mobility, but across countries. So I thought that was, I don't believe we ever pursued like, any sort of microfoundations for that particular approach. My question is actually more naive. So from what I understand, the results that you got are pretty much contingent on having discrete levels of human capital attainment, right? And if I understand from your model, the way to attain different levels of human capital is going to be funded by dynastic wealth accumulation, right? So individual dynastic wealth accumulation. Would your outcomes change, or would it be so dependent on having discreteness if we're thinking about a process that's about collective bargaining, where we're thinking about the production of human capital as a public good? So some form of public schooling, for instance, and a process that determines, the level of public schooling at different locations, for instance. As we know, public schooling is still locally funded, right? And so I'm wondering if that might be the case where, so do we need like discrete levels of attainment, or could it be, for instance, where these discrete levels are an equilibrium outcome of this bargaining solution across various locations, say, at the school district levels, for instance. Thanks.
Yeah. Well, so the answer I would give there is that that's when one has a social model of intergenerational mobility, so neighborhoods model. So models that I've written, for example, there all the action has to do with the degree of economic segregation across the school districts. So in other words, once you have social determination of human capital, it doesn't have to just be public finance; it can be social interactions. Then the key question becomes, what is the degree of economic segregation? But that would certainly, but that also discretizes the investments, the differences in the public goods. So in that sense, you could get that. It's a completely different model because everything is contingent on the level of segregation. Okay, well, thanks to all of you, and I'm going to ask my colleague, Professor Masumi, to take the floor.